Okay, so let's unpack this today. We all know the basic dividing line in the silicon world.
Right.
For decades, it's been x86 architecture ruling the desktop and the data center, and then ARM architecture ruling the smartphone in your pocket.
Yeah, the classic narrative.
It's a very well-worn narrative, but today's deep dive takes that basic premise and just throws it into a hyperscale blender.
It really does.
We are dissecting this very specific, honestly, incredibly provocative set of talking points from a source called USAVisible.
Mm.
And what starts as a fairly standard set of questions about CPU architecture rapidly spirals into this existential crisis for the entire tech industry.
Yeah, it goes from microchips to the water supply pretty fast.
Yeah, touching on municipal water supplies,
Sure.
legacy software baggage, and ultimately, like, literally putting data centers in orbit.
The trajectory of this document is what makes it so compelling, I think.
Yeah.
Because USAVisible manages to connect these microscopic atomic-level differences in how a microchip processes a line of code to macro-level environmental and logistical tipping points. Right.
It reads less like a spec sheet and more like an autopsy of the current AI boom.
Exactly. So rather than just reading down their list, let's look at the core mystery that they're setting up here.
Okay.
Because they start by asking us to revisit the fundamental difference between an ARM CPU and a regular x86-64 CPU.
Right, the basics.
Yeah, and I think we need to get away from the cliche analogies here. Like, we aren't just talking about a heavy diesel engine versus a sleek magnetic motor. The difference is really in how they are instructed to think.
Right, because we are dealing with CISC versus RISC architecture.
Right, and break this down for a second.
Sure, so that's complex instruction set computer for x86
Okay.
and reduced instruction set computer for ARM.
So let's visualize that. Think of x86 as a massive, heavy-duty Swiss Army knife.
I like that.
It has a specific dedicated hardware tool built into the silicon for almost every conceivable software instruction. Right, so if a program needs to execute a highly complex, multi-step mathematical operation, the x86 chip likely has a specific physical circuit designed just for that one operation.
Exactly. It can execute that complex command in a single clock cycle.
But the trade-off for having all those dedicated tools built into the silicon is physical bloat.
Right.
And x86 processor requires billions of intricate transistors to support that massive instruction set.
And more transistors firing means more electricity consumed?
Yeah, and more electricity consumed means more heat generated. It's just unavoidable physics.
Unavoidable physics, which brings us to the ARM approach, which is more like the master carpenter.
Right.
Instead of this bulky Swiss Army knife, the ARM chip walks into the workshop with just a hammer, a saw, and a measuring tape.
The basics.
Just the basics.
Okay.
It has a radically reduced set of instructions. It doesn't have a dedicated hardware circuit for every single complex operation.
So if it needs to do something complicated, it uses its basic tools in rapid succession to get the job done.
Right. And because it has far fewer complex circuits baked into the actual silicon, an ARM chip is incredibly lean.
Super lean.
It requires significantly less power to operate, and therefore it runs fundamentally cooler.
Which is exactly why ARM conquered the mobile market.
Yeah.
I mean, when your power source is a tiny lithium-ion battery and your cooling system is literally just the aluminum casing of a phone, efficiency is the only metric that really matters.
But USAVisible isn't interested in our phones here.
No, they're not.
They immediately pivot to the software ecosystem. They ask flat out, can ARM run native x86-64 software?
And we know the native answer is a hard no.
Right. They do not speak the same language at all.
Yeah.
The master carpenter doesn't know how to use the Swiss Army knife instructions.
They are completely alien to one another. Like, the binary code that's compiled for an x86 processor is expecting to find all those complex hardware pathways.
Right.
So if you feed that same code directly into an ARM processor, it just hits a wall. The circuits it's looking for literally do not exist on the chip.
Which makes their next question, which is faster, ARM or x86-64. It feels like a highly loaded trap.
Oh, absolutely. Because fast is entirely relative here.
Right.
Natively, if you build an operating system from the ground up to speak ARM's language, it flies.
It flies, yeah. But we don't live in a vacuum.
Right.
We live in a world where the vast majority of enterprise software, financial databases, legacy code, it was all written explicitly for x86.
Yeah, decades of it.
Decades of it. So theoretical speed doesn't matter if the chips can't natively talk to the software that's actually running the global economy.
And that tension is really the fulcrum of USAVisible's entire argument here.
Yeah.
They're establishing these technical boundaries before introducing the real-world variables. We have this lean, cool, highly efficient hardware architecture in ARM, but it is locked out of the dominant legacy software ecosystem natively.
Right. And here is where the document takes a really sharp turn away from theoretical computer science and gets into the reality of modern hyperscale computing.
Yeah, this is where it gets real.
USAVisible drops a roll call of tech giants. They specifically ask, do TPUs, Apple chips, NVIDIA, OpenAI, Tesla, XAI, and others use ARM?
That grouping is incredibly deliberate.
Yet notice who is missing from that list.
Right.
They aren't talking about companies making budget laptops or smart refrigerators.
No, they're pointing directly at the vanguard of artificial intelligence, autonomous driving, and heavy-duty data processing.
Exactly. So you have Apple, which successfully transitioned its entire consumer lineup to custom ARM silicon.
Right.
But then you have NVIDIA, the undisputed king of AI hardware. You have OpenAI and XAI, the companies currently training neural networks with hundreds of billions of parameters.
Right. Massive scale.
Tesla is processing massive amounts of visual data for self-driving. Google's TPUs, their tensor processing units, are crunching just mind-boggling data sets.
Yeah.
These are the absolute heaviest hitters in the infrastructure space.
And by highlighting them, USAVisible is forcing us to recognize that ARM has escaped the smartphone. It's being deployed as the foundational architecture for the most computationally demanding tasks in human history right now.
But the immediate question is why? Why take a mobile architecture and force it to run trillion-parameter AI models?
Right.
USAVisible poses the core motivation. They ask, did those companies switch to ARM because they thought it would solve CPU heat?
It sounds reductive at first glance.
It really does. When I first read that, I couldn't help but push back a little.
Yeah.
I mean, are we really supposed to believe that a multi-trillion-dollar, industry-wide architectural pivot by the most resource-rich companies on Earth boils down to basic overheating?
Right.
It feels like saying we transitioned from coal to nuclear power just because we got tired of wiping soot off our windows.
Yeah, it sounds too simple.
Like, there has to be a deeper logistical reality at play here, you know?
Well, the skepticism is warranted, but we have to translate what heat means at the scale of an NVIDIA or a Google data center.
Okay.
Heat isn't just an annoyance for them. It is the absolute hard ceiling on computational growth.
Because of rack density.
Precisely. Rack density. If you are building an AI supercomputer, your goal is to pack as many processors as physically possible into a server rack.
To minimize the distance data has to travel, right?
Exactly. But by 86 processors, with their massive power draw and complex architecture, they generate a staggering amount of thermal energy.
Yeah.
If you pack too many of them into a single rack, the silicon will literally cook itself to death.
So the servers throttle their own speed to prevent melting.
Yes, so the only way to scale up an x86 data center is to spread the servers out.
Which increases latency.
Which increases latency, right. And then you have to pump in massive industrial-scale air conditioning.
Right, the chillers.
The electrical cost to run the chillers often rivals the electrical cost to run the servers themselves.
Wow.
So when USAVisible asks if they switch to ARM to solve CPU heat, they're really asking, did the AI industry realize that x86 was going to literally melt down the power grid before it achieved artificial general intelligence?
They hit a thermodynamic wall. And ARM, with its lean RISC architecture, promised a way through that wall.
Yeah.
Lower power draw per chip means less heat. Less heat means you can pack more chips into a rack. More chips per rack means faster training times for AI models.
All while theoretically saving a fortune on the electricity bill.
It sounds like the perfect solution.
It does. It sounds like the necessary evolution of hardware.
But here is the massive disconnect. And this is where the USAVisible document goes from a tech analysis to basically a thriller.
Yeah.
If ARM is this hyper-efficient savior, why does the source immediately follow up by asking what actually happened when they ran ARM at scale? Did energy, cooling, electricity, and water costs go up?
That is the ultimate twist in the narrative here.
It defies logic. You rip out the hot, power-hungry x86 chips, you install the cool, efficient ARM chips, and your utility bills skyrocket.
Right.
And it's not just electricity. USAVisible specifically calls out water costs. That's a detail that really grounds this in physical reality for me.
Oh, absolutely.
We aren't just talking about spinning fans in a server room. We are talking about evaporative cooling towers.
Massive data centers use millions of gallons of water to manage heat.
Millions.
They literally pump water through the facility to absorb the thermal energy from the servers and then evaporate that heated water outside to cool the system down.
Which means if an AI facility moves into a region, it can genuinely threaten the local municipal water supply.
Yeah, it's a real issue.
But again, if ARM is supposed to run cooler, why is the water boiling away faster? Why are the grids straining?
USAVisible pinpoints the exact mechanism of this failure in their next question.
Okay.
They ask, is the real ARM problem the translation layer that has to read by 8664 software?
The translation tax.
The translation tax. This is exactly where the hardware dream crashes into the software reality.
Let's break down exactly how this emulation works, because understanding the mechanics here explains the entire energy crisis.
Sure.
So we established that ARM cannot natively read by 86 code. The master carpenter doesn't understand the Swiss Army knife instructions.
Right. But as we said, the entire world runs on by 86 mode. You can't just pause the global economy while every single software developer rewrites millions of lines of code from scratch for ARM.
No, you have to run it as it is.
Right. So you introduce a translation layer, an emulator,
Right.
a piece of software that basically sits between the by 86 code and the ARM hardware.
Yeah.
When the legacy program sends an instruction, the translator catches it midair. It reads this highly complex by 86 command, frantically scrambles to break it down into a sequence of simpler ARM commands, and then feeds those to the processor.
And it has to do this for billions of instructions per second in real time.
And that frantic scrambling, that requires computational work.
Massive amounts of work. It's an incredible irony, really. You buy the ARM chip to save power. But now, before the chip can even begin to do the actual task you want it to do, whether that's serving a web page or training an AI, it has to expend huge amounts of energy just translating the instructions.
The processor is working twice as hard just to figure out what it's supposed to be doing. Think about the clock cycles. An by 86 processor might execute a complex math equation in one cycle because it has a dedicated circuit for it.
Right.
The ARM processor might need 5 cycles to do the exact same equation. But with a translation layer, the emulator has to figure out that mapping on the fly. That translation overhead eats up processing power.
And what does processing power generate?
Heat.
Heat. It brings us right back to the very problem they were trying to solve in the first place.
Yeah.
The translation tax completely destroys the underlying efficiency of the ARM architecture.
Right.
At scale, when you are running an AI data center the size of a football field, the sheer physical energy required just to translate old software into new hardware is literally boiling the cooling water and draining the local power grid.
It is a profound logistical trap. USAVisible is pointing out that the tech giants attempted a hardware bypass for a software problem.
Yeah.
They tried to out-engineer legacy code with more efficient silicon, but the friction of translation is purely physical. It manifests as thermal energy.
Which leads us to the final and, frankly, most wild segment of the USAVisible document.
Oh yeah, this is where it gets crazy.
Because if the translation layer is creating this unsustainable thermal runaway, how do you fix it? The tech giants can't just stop building AI.
No, the train has left the station.
Right. So USAVisible asks, what is the solution?
And the options they present range from the vastly expensive to the downright interplanetary.
Seriously. So let's start with the earthbound solution. They ask, would server motherboards have to be redesigned?
That is the pragmatic, yet still incredibly painful engineering answer.
But what does that actually mean in practice? Like, redesigning a motherboard sounds like something a PC builder does in their garage. At this scale, what are we talking about?
We're talking about ripping out the underlying physical infrastructure of the internet.
Wow.
Current data center motherboards, bus architectures, and memory interfaces have been heavily optimized around the by 86 paradigm for decades.
Right.
If you are going to truly unlock ARM's efficiency at a hyperscale level, and perhaps build hardware-level translation accelerators directly into the boards to bypass the software emulation tax entirely, you have to reinvent the server rack from the ground up.
It's throwing away billions of dollars in sunk costs.
Absolutely.
It means admitting that the current hardware ecosystem is fundamentally broken for the software reality we inhabit right now.
Yeah.
It would require this massive coordinated effort across competing manufacturers just to standardize a completely new architectural paradigm.
Which is why, perhaps, USAVisible immediately pivots to an alternative that bypasses earthly infrastructure entirely.
Yes, the final question. The absolute logical extreme of this entire deep dive.
Here we go.
They ask, or are data servers in orbit like a space station the best answer for energy and heat?
It's a stunning escalation.
I have to be honest, when I first processed that line, I thought it was a joke.
Yeah.
But if you follow the breadcrumbs USAVisible just laid out for us, it
Right.
makes a terrifying sort of sense.
It really does.
Have the thermal limitations of our silicon, compounded by the translation tax of our legacy software, become so energetically burdensome that launching literal server farms on rockets into the vacuum of space is considered a viable alternative to just fixing the code on Earth.
Well, let's analyze the physics of that proposition because it's actually not entirely science fiction.
Right.
Why space? First, unlimited, unobstructed solar energy.
Oh, right.
You bypass the terrestrial power grid entirely. You don't have to worry about local zoning laws or drawing down municipal reservoirs for cooling water.
But wait, what about the heat? The vacuum of space is cold, sure, but it's a vacuum.
Right.
It's a perfect insulator, meaning a thermos flask uses a vacuum to keep your coffee hot. If you generate massive amounts of heat inside an orbiting data center, there is no air or water to carry that heat away.
Exactly. You can't just open a window up there.
No.
You would have to deploy massive, complex radiator arrays to radiate the thermal energy away as infrared light. It is an incredibly difficult engineering challenge, and that's before we even discuss the latency.
Right, latency. If I'm querying an AI model, my data has to travel up to a low Earth orbit station, get processed, and beam back down.
Ooh.
The speed of light is fast, but distance adds latency.
But compare that latency to the computational drag of terrestrial emulation.
Oh,
That is the calculation USAVisible is forcing us to make here.
okay, yeah.
Is the friction of translating by 86 code on Earth so severe that the round-trip latency to a space station is actually a competitive alternative?
It just highlights the sheer scale of the desperation. The fact that a document analyzing CPU architecture ends by casually floating the idea of orbital data centers tells us everything we need to know about the severity of the energy crisis facing the tech industry.
It's a brilliant narrative arc within basically a 13-line document.
Yeah.
USAVisible takes us from the micro to the macro. They demonstrate that the friction between a new, efficient technology and an old, entrenched standard isn't just a glitch on a screen. It manifests as a massive physical drain on resources. We think of the cloud as this ethereal, invisible thing.
Yeah, the cloud.
But the cloud is heavy, it requires land, it requires rivers of water, and it requires vast amounts of power.
It really is a wake-up call wrapped in a tech spec sheet.
Yeah.
They took a microscope to a microchip and showed us how it's literally boiling the planet.
Yeah.
And it's fascinating how USAVisible chooses to close out this really intense sequence. The very last line of the source is just a simple sign-off. It says, "Thanks for watching the USAVisible podcast. Tell us what you think."
They just lay out all the evidence of a massive industry bottleneck, offer two totally extreme solutions, and then step back, leaving the implications just hanging in the air.
Which brings us back to where we started today.
Yep.
The heavy, complex x86 architecture versus the lean, efficient ARM architecture. We've unpacked the speed, the tech giants, the heat, the translation tax, and the extreme solutions.
We covered a lot of ground.
We did.
Yeah.
But as we wrap up this deep dive, it leaves me with one final thought to mull over, building directly on that orbital space station dilemma.
What's your takeaway?
If the brightest minds at the most powerful tech companies on Earth are potentially willing to consider the unimaginable, launching thousands of servers into the freezing vacuum of orbit, dealing with rocket launches, space radiation, and massive radiator arrays, all just to manage the heat generated by their chips.
Right.
What does that actually say about our stubborn reliance on old software?
Yeah.
Are we literally running out of room, water, and energy on this planet simply because we refuse to rewrite our legacy by 86 code? Are we seriously going to push our digital infrastructure into the stars just so we don't have to abandon the software of the past?
It is a profound question about technical debt.
It really is. We are letting the ghosts of old code dictate the future of our physical infrastructure. And like USAVisible said at the end of their list, tell us what you think.